Can you guys see my screen? Okay. So, our topic was from for the final. We're going to start from lecture 7 and we're going to study till lecture 16, right? So, what I will do from lecture 7, 8, and 9, I will cover each chapter briefly after each class because these were the post meet classes. Okay. Yes, Shihab. Lecture 9, right? Okay. I will start from lecture 9. I will uh, start from lecture 9 and 10, right? Okay, right. So your mid final syllabus will only include the parsing of a SLR grammar, given that you already have a parsing table, right? So you do not need to construct the LR0 items or the automaton, and you also do not need to construct the parsing table. This will be given. You just need to simulate the parsing table, right? So, given a string, you just need to show that if that string is parsed by the parsing table or not. So, this is a very simple thing. So, what we'll do, we'll have around 8 classes. So, from lecture 10 to lecture 16, there are 7 classes, right? So, we'll cover these lectures and we'll try to have one online quiz, and during that quiz I will just uh, show the simulation of the parser, right? So how can you parse given a table and a string and show if the string is parsable by the grammar or not. Okay. So or I what I can do is I can make a simple video and share it with you. Okay. So that should not be an issue because this is the basically only one lecture from the pre-mid syllabus, right? So this shouldn't be an issue. Even though lecture 10 was covered before mid, but that was long ago. I'm going to cover lecture 10 today. So this is a very simple lecture, and after that we'll have lecture 11, 12, and 13. Okay, so these lectures are closely related with lecture 10, right? So you need to understand the basic of syntax directed translation to actually do uh, type and attributes of grammar, and how actually the array are being calculated in a compiler, or how uh, types are being checked in a compiler. Okay, so this chapter, lecture 10, is the basic foundation for the next few lectures. I think before meet I have also covered lecture 11 as well. So S attributed definitions and L attributed definitions, right? So the next two lectures should not be that hard. um, if you have taken notes, you can check your previous notes, but uh, I'm also going to discuss this in details in these classes. Okay. So, if you guys like to share anything, feel free to share before I start the class. Any concerns? Yes. this is basically an assessment বিকজ আমাদের তো মিট হয় নাই, সো মিটের পরবর্তীতে ওই অ্যাসেসমেন্টটা দেওয়া হয়েছে। না, দিস উইল বি অ্যান অ্যাসাইনমেন্ট। ওকে, সো ওইটাই বললাম যে ইউ উইল গেট টু নো অ্যাবাউট দিস অ্যাসাইনমেন্ট অ্যাট দ্য থার্ড উইক, স্টার্টিং অফ দ্য থার্ড উইক or the ending of the second week. Okay. Okay. Okay, so let's get started with syntax directed translation. So you have already done lab 2, right? So in lab 2, what we tried to do, we had some grammars for a subset of C language. In that grammar, we tried to find out when a production rule is being reduced to its production head, right? And we also had some actions in our grammar, and we wrote that at this point this rule is being reduced to this production. So semantic rules or actions, whatever you say, we are already familiar with this, and we have already seen this in our lab 2, right? So what are syntax directed definitions and syntax directed translations? So syntax directed definitions are basically production rules. So these are the production rules from your context free grammar, right? In context free grammar you had some production rules that define a language, right? So syntax directed definition is basically a list of productions that has some semantic rules. For example, here we are saying E produces E plus T, and with this production we have some associated rules. So we have basically seen this E stands for any type of expression, and this T stands for any type of term, right? So it can be addition, the term can be addition, the term can be subtraction, right? Or the term can be multiplication or division. We only have seen the addition and multiplication expression grammar, right? So here we are saying this expression can have another expression added with another term. So this term can be either plus or minus. So this term can be further deconstructed into term into a factor. This factor can be a simple identifier, which can be A, B, or C, or any identifier, right? So, or it can be a term plus another identifier. So, we are basically building an expression. So, suppose our expression might end up looking like this: A plus B multiplied with C. So, this will be our expression. So, what? Okay. Is it visible now? Okay, thank you. So, as I was saying, this term can be either T into F. F is a factor, and F can produce ID. So ID is basically an identifier. It can be A, B, C, or first name, last name, right? So it can be an identifier. So this T can be T into F or T plus F, right? So in the end, we'll get an expression. This expression can be A plus B into C minus B, right? This is only one rule of the grammar. If we see the entire grammar can produce this expression, right? Okay, so what does this semantic rule mean for this production? Here we have a production: E produces E plus T. So this one here, so if you can see, this one here basically denotes if this E is on the right hand side or the left hand side. Both E are the same, right? So this one basically means it is the production body. This E is in the production body, nothing else. Okay, so what does this mean? Suppose uh, our expression generated by this grammar is A into C plus B into C, right? So this is our expression. So what does this semantic rule means? This semantic rule basically means this expression, suppose this expression will have a code. This is an expression, right? For compiler to understand this, it should have some kind of code related with it. This is basically a normal production. This will have some code associated with it. Okay. Similarly for this E and this T as well. Okay. So what it is saying, so the three address code generated by this E is actually the code generated by this E concatenated with the code generated by this T concatenated with a plus, right? So you might say, why there is no plus in the between of these two codes, right? E1 code and T1 code. Suppose this is your, this part is your E1 and this part is your T, right? So why there is no plus in the between? So again, this vertical or sign is basically means concatenation. This is not a or sign, this is basically concatenation, right? Those two slashes means we are concatenating the code. So compiler has a task which is to generate three address code, right? So to basically we are concatenating those codes. Okay, and this semantic rule is basically for postfix notations, right? For postfix notations, we write the operands first, and last we write the operator, right? So suppose you have A plus B as a notation, and if you want to write the postfix notation of this, you will write A B plus. Okay, because sometimes it is easier for the computers to read the postfix or prefix notations rather than the actual expressions. Okay, so we are basically using these semantic rules to ultimately generate the three address codes. So any questions so far? Okay. So if you remember, there were phases of compilers, right? So compiler first had to go through lexical analyzer. The string was provided to lexical analyzer. Then the lexical analyzer would do syntax analysis. Then the syntax analysis would do semantic analysis. And the after checking after doing the semantic analysis, you will provide a high level code, and it will try to convert those code into a assembly language code, right? You have already seen what does assembly language code looks like, right? You have done the microprocessor course, and you already know what the assembly language code looks like. So suppose this is an assembly language code at bl comma cl, right? Okay, so here BL is a register and CL is a register. So this instruction means whatever value is stored in BL register, add it with the CL register and store that value inside BL register. So suppose BL register has 5, CL register has 6. So after running these instructions, we'll calculate the CL value and BL value and add them, which is 11, and store that 11 into BL register, right? Is this part clear? Right. So these assembly codes are then break down into machine language codes, and this machine language codes consist of zeros and ones, right? So these zeros and ones are basically same instruction as this, and you might have also learned how to convert those 8086 assembly codes into machine language code using a template, right? Right. So our task of the compiler is basically after doing the semantic analysis, right? Semantic in again, let's go through this. In lexical analysis, compiler checks if your tokens are valid or not, right? Whatever things you are writing in a code, is it valid or not? Okay. uh, okay, suppose you have written this type. Okay, so lexical analyzer will check if this type is basically within a keyword or not, or is it a valid lexeme or not, right? So after checking that, it will provide the tokens, it will provide all the tokens into syntax analyzer. So suppose this is a JavaScript language, right? So this extension is .js, so this is a JavaScript language, right? uh, this language has a compiler of its own. So the syntax, what syntax analyzer does is it checks whatever token you generated, whatever token you have generated is matching with the rules that the JavaScript grammar has, right? It will check, suppose you are using this keyword const, right? And you are writing a identifier after this, right? And you are writing equal and you are using the new keyword. So it will check with the rules if you can do it like this, and it will say if it is correct or not, right? So that is the part of syntax analyzer. And for semantic analyzer, it will check if the logic of your code is correct or not. Suppose you have some integer, you have some variable declared as integer in text, and after a few lines you are trying to assign a float into a integer variable. Suppose 10.12, you are trying to assign it into a integer variable. Is this correct? Can anyone please reply if it is correct or not? Can you hear me? Can you hear me? Okay, so is this correct or not? We have declared an integer variable and we are trying to assign a float value to an integer variable. Is this correct? Right. So this is not correct, right? So what semantic analyzer does is semantic analyzer checks if your logic is correct and if your type, whatever type you're assigning to a variable, whatever type you're assigning into your code is correct or not. After it is done checking all that, your code is ready to convert it into a assembly like code, right? It cannot directly convert it into a assembly code. Okay, the compiler cannot directly convert it into the assembly code. The last part of your compiler is basically converting it into an assembly code. Then the assembler takes that assembly code and it converts it into a machine language code. So after semantic analysis, what your compiler will do, it will try to create those codes into a similar form of assembly codes. Those codes are known as three address code. Suppose you have uh, some variables like this, some expression like this: a plus b minus c into d, right? So in assembly language you can see there are there is one instruction and two operand, right? So it basically consists of three things. So can you do this whole expression in one single line of assembly code? Is it possible? Sorry, I didn't get you. Right, it's not possible because in assembly languages you have instructions like add, sub, mal, div, right? So you cannot use all those uh, keywords in one instruction. Can you do this? Add, suppose some, you wrote some registers, then you wrote sub, and you wrote some register. Is it a valid assembly instruction? Is it? Right. So you cannot write this expression in one instruction, right? So what your compiler does is it's convert this expression into some form of similar codes. Those codes are similar to your assembly language, right? So those codes are similar to your assembly language. So for example, it will convert it into a three address code like this. Suppose it will take a temporary variable t1 and it will store a plus b in it. Then it will use this expression and store it into another temporary variable, suppose t2, right? So it will compute c into d. Now what you need to do is subtract t2 from t1. So you can take another temporary variable t3 and do t1 minus t2, right? So this t3 represents this expression. Is it right or not? Right. So any confusion so far? Right. Okay, so if you can see now, this t1 can be easily converted into a three address code, right? So suppose a1, the value of a is stored in some register, the value of B is stored in some register, right? So we can easily convert this into a three address code. For example, this instruction add BL comma CL. So in this case, A will be BL, this plus will be add, right? And this B will be CL, right? And we are storing the value in BL. So this T1 will be BL. So we can easily convert this into a assembly code, right? So compute your compiler goes through the three address code process. Okay. So this semantic rules. uh, did I remove the PDF? Here's the PDF. Okay. So this semantic rule is basically helping you to generate a three address code. Okay. So is it clear? Uh, you No, no, no. We'll discuss this in details when you talk about three address code. So three address codes are basically like this because you have two operands. Okay, you have two operands and one operator. Okay, two operands and one operator. At most, there can be only one operator. Okay, so these assigned parts are not necessary. When we study about three address code, you will see that part is not really needed. Okay, so here we're saying we're assigning this value to T1, we're assigning this value to T2, right? So this assign part is not needed because what the machine does, it stores this value into some memory address. Okay, and later uses the memory address for another calculation. So we'll get to more details when you study about three address code. Let me see. I think uh, you'll be able to cover three address code in this semester. Yes, right. So three address code is in lecture 15. So you'll be able to cover or learn about three address code in the future classes. Okay. Right. So we have covered this in the pre-meet class, right? But we have not covered it in details because after meet we plan to cover this as well again. So now you can understand what these semantic rules are used for. So suppose when your compiler is matching with these productions in the semantic analyzing phase, sorry, syntax analyzing phase. So in lab 2, what your compiler was doing in semantic analysis phase, your compiler was checking if those tokens are being matched with the provided grammar rules or not, right? So in this process, by using these semantic rules, it can also generate a three address code that can be later converted into a assembly code. Okay, so this is basically syntax directed definitions. So syntax directed definition is nothing but your production rules with some additional semantic rules. So if you read about the description here, you will see syntax directed definitions are nothing but productions with semantic rules, right? Okay, then what are syntax directed translations? So syntax directed translations are nothing but the uh, implementation of syntax directed definitions. right? So we have production and a semantic rule associated with it, right? So whenever we're doing some syntax analysis, we can implement those semantic rules to generate three address code, or to generate or to check if the logic is valid or not, or we can check if the type is correctly being assigned or not. So in your lab 3 you'll see, while doing syntax analysis, you will check if the assigned value or assigned type into your code is correct or not, right? So that is basically syntax directed definitions and syntax directed translations. So syntax directed translations, these semantic rules are basically enclosed in a square braces, and this is not known as semantic rules anymore. This is known as semantic action, right? So we have seen in lab 2, after writing the production rules, you need to give a colon, and after that you need to have a square braces, right? So these were known as actions. So these are basically your semantic actions. So instead of semantic rules, you can simply convert this semantic rule into a semantic action, like uh, print e dot code concatenated with t dot code concatenated with plus, right? So this can be converted into a semantic actions as well. Okay. Now, uh, if we go into details, right? If we go into the details of semantic rules, so here we can see, in semantic rules, each terminal or non-terminal, right? So each terminal or non-terminal can be associated with an attribute, and this attribute is basically written after a dot, right? So your this non-terminal e will have a dot, and after that will write something. So this is known as the attribute. So semantic rules are consist of your terminals and non-terminals and attributes of those terminals and non-terminals. So your context-free grammars will have rules, right? Right. So this is your CFG. If you do not remember, let's recall. So in your CFG, you will have some uh, rules, right? So these rules can be numbered, right? So these rules can be numbered as well. So this is the starting symbol, because this is the first rule, right? So this is the starting symbol. Again, in your CFG, you have this production sign. This basically reads produces, S produces E, right? So you have a production sign, and you have production head, and this part of this is production body. So uh, your right side is production body, and left side is production head, right? So the very first rule, the production head of the very first rule, is the start symbol. So here, this S, this E, this T, these are basically your non-terminals. meaning you can expand those non-terminals again, right, into different rules. And your plus, multiplication, and these IDs are basically your terminals. So you cannot uh, you cannot expand your terminals, right? Unlike your non-terminals, you cannot expand the terminals. So any questions about how CFG looks or works? No, right? So let's take this rule for example, rule number 2. So from this CFG, I have taken this rule. So I am going to create a semantic action for this rule, right? So semantic action will consist of terminals and non-terminals of the rules. So in your semantic actions, you will have terminals and non-terminals, and these terminals and non-terminals can also have an attribute. For example, this expression has an attribute code. So e dot code is equal to, let's name this e1. So e1 dot code plus t dot code. So we can remove this plus and we can write concatenation here or whatever the rule suggests, right? So if you can look at this semantic rule, you see it has terminals or non-terminals. For example, e is a terminal here, non-terminal here, and the plus is the terminal here. And along with this terminal, it will have some attributes. We write those attributes by appending a dot before it, right? So this means this attribute, this code is an attribute. It is the attribute of non-terminal e. For example, the plus can also have an attribute. So suppose uh, we are concatenating them, right? So we are concatenating them. So this value stands for concatenation, right? So this plus can also have a code, right? So this non-terminal can also have a code. For example, the code for plus is simply a plus sign, right? And we concatenated with a t dot code, right? So here it can also have an attribute, but it is not necessarily that all the terminals and non-terminals can have attribute. Okay, so semantic rules are basically rules that have terminals and non-terminals, and those terminals and non-terminals can have some attribute, right? So what is this rule? This rule is basically saying whatever the attribute of this non-terminal will assign some value to it. What that value will be? That value will be the concatenation of these three values, and these three values are basically the attributes of these three terminals and non-terminals. Okay, is it clear? Yes, Nafis. Now it can be anything. It can be anything depending on your semantic. It can be anything. It can be e dot e1 dot value for values, right? Or suppose this e has many variables assigned with it. Okay, so suppose not for this example. Suppose we have some rules, and in this rule, this e can have multiple values, multiple variables. So you can write variable, or it can have arrays of variables. So you can write, so from that array of variables, use the zeroth variable, right? So it can be anything. Those semantic rules can be anything as long as you define them correctly, right? Sometimes it will be defined for you, sometimes you need to define it. or sometimes you need to fill in the blanks. Suppose you have some semantic rules given, and seeing those semantic rules, you need to uh, provide some missing semantic rules. But those are very rare, right? So in most cases or during your exam, you will be given those semantic rules, right? For every cement sorry for every grammar rules or production rules, you will be given some sort of semantic rules that you can use to generate something. That can be three address code, that can be some sort of calculation, that can be some sort of validation, right? So we can also use these semantic codes to verify. So suppose we have a grammar for expression, right? So using this grammar we can create an expression. So suppose we can create an expression like this. uh, so suppose instead of id it is a number. So instead of generating variables, it will generate numbers. So suppose 2 plus 3 uh, plus 5 plus 6, right? So this string can be generated by this grammar, right? Yes or no? Right. So if we generate these strings, right, most probably not, because you need some other grammars as well. So e can generate e, then t can generate t, right? Now you can generate this string using this grammar. So what is the value of this expression? What will be the value of this expression? Anyone? So this is 6, and we add 5 plus 6 to the remaining 6, right? So this gives us 17. So does your compiler need to convert this into a three address code and then use the machine to generate it? It might not need it, because we can use the semantic rules. We can use the semantic rules to calculate its value, right? So when it is in t into f, we can say t dot value into f dot value. So that will give us 6, right? Whenever it is this, e e dot value plus t dot value, then the value of t is 6 and the value of e is 5. So we can say 5 plus 6 is 11. Again, for this example, the value of t is 11 and the value of e is 6, right? Sorry, the value of e is 11 and the value of t is 6, right? T can produce it. So by doing this, using the semantic rules, we can calculate the value of this expression. Okay. So these semantic actions have various purposes. You can generate three address code from it. You can generate uh, or you can evaluate expression using it. You can create DAG, that is known as directed acyclic tree. This is another representation similar to a three address code. Compiler can use DAG to generate assembly code as well, right? So these semantic actions has various purposes, right? So these semantic rules and actions have various purposes. Not like they will always calculate the three address code or calculate or evaluate the expressions. Yes, Anis. It doesn't matter. Boe, basically this semantic rule is in postfix notation, right? So I wrote it as infix notation, meaning your operand will be the middle of the two operators. it is written in this way because it is easier for machine to understand the expression if it is written in postfix notation. Clear? Any more questions? Any questions, everyone? So far, any questions? Okay. So, so whatever I said so far is written here, right? Is written here, and it is written in bookish statement, right? So you can go through this again to refresh what I have just said, or you can watch the recording. Okay. So, so this is basically the logic of syntax directed translation, and the evaluation of syntax directed translation we'll see in this part, right? So I have said you can evaluate the grammar as well, right? We'll see it in this part as well, right? In this part we'll see how it actually evaluates the expression, right? What I have just talked about, we'll see it in details. But before that, we need to learn two important things. Those are these uh, uh, the attributes that I have talked about. The um, semantic rules are associated with attribute values, right? So these attributes are of two types. One is a synthesized attribute, and another is an inherited attribute, right? So from this grammar, suppose you have a grammar. This let's take a good example. Suppose you have this grammar, right? So suppose you have this grammar and you are asked to generate this string using parse tree. Can you do it? Can you generate this string using a parse tree? We have already seen this before, right? Before the meet, we have already seen this. So this is the parse tree by using which we can generate this string, right? So So this is the pass tree for this expression, right? You have some production and you have some uh, s- string that you need to generate using this production, right? So by first using this, by first constructing this parse tree, you can generate this string from this grammar. Is it true or not? Any questions regarding this? If you do not remember how to construct the parse tree from a production, please let me know because this is important. We have this grammar and we need to construct this string using these production rules by a parse tree. So this is our parse tree and we have made the this 3 multiplied by 5 plus 4n, right? Any questions on this? If you do not remember how to construct the parse tree, please let me know. Anyone who doesn't remember? Okay, so we are all clear on this, right? Okay, okay. So this is basically my production, right? And you can see these are basically, so these are basically my non-terminals, and this plus, this n, multiplication, opening braces, closing braces, digit, these are basically my terminals. So in semantic rules, your attributes can be of terminals and non-terminals. Your terminals and non-terminals can have attributes, right? So when you construct a parse tree and you write those attributes, when you construct the parse tree and you write those attributes, suppose here L has an attribute value, E has an attribute value, right? T has an attribute value, F has an attribute value, digit has an attribute lex value. So here you can see digit is basically a non-terminal terminal containing. So digit in this case is basically a non-terminal, is basically a terminal containing an attribute. So far we have only seen the non-terminals containing the attributes, right? Now we can see this digit, which is a terminal, also has an attribute, right? So this is basically your production. This is basically your semantic rules, and we have some attributes. So now these attributes, so this value, these attributes can be of two types, right? It can be synthesized attribute, it can be inherited attribute. So what are synthesized attribute and what are inherited attribute? So suppose this is basically a production rule, e into e produces e1 plus t. So to generate this, you need to construct a parse tree, and in that parse tree there will be some node like this: e produces e1 plus t. Yes or no? When you construct a parse tree to represent this string, your parse tree will have some sub node or some node looking like this, right? If you can see example here, so here you can see this sub node is exactly what I have drawn here, right? So now how do I figure out this value, and this value? How do I figure out, are these attributes synthesized attribute or inherited attribute? So for each node, I can only figure out the production head attribute. So I can only figure out from the production head attribute if it is synthesized attribute or it is inherited attribute. So I can only figure out from this diagram that this E will have a attribute which is value. I can only figure out if this value is synthesized or inherited. How I can figure out? I can figure out by looking how this value is being calculated. So this is a attribute. So this attribute is being calculated like this. So as you can see, this value, this value is being calculated by value attribute of E1 and attribute of T. So now we need to see where the attribute of E1 and where the attribute of T's are. Here is the value and here is the value, right? So these attributes are the children of this node, right? So E1 is children of E and T is also children of E. So when the value of E is being calculated by the attributes of its children or the attributes of itself, then it is known as synthesized attribute. Meaning the value of E, this E, must be calculated by its own attribute value or the attribute value of its children. Here in this case, E and T are its children. So this is synthesized attribute. Okay. And similarly for inherited attribute, the values must be calculated from its parent or itself. The value cannot come from its children. So suppose S produces E and E produces AB, right? So this is another grammar. So E will have a attribute, suppose value. A has an attribute, suppose value. B has an attribute, suppose value, right? Okay. And S has an attribute, suppose value. Now we are saying E dot value is equal to S S dot value plus E dot value. So is this synthesized attribute or inherited attribute? But E involved থাকলেও all the other values must be its children. Okay, even if E is involved, all the other values that are being used to calculate the value of E should be its children. Is S the child of E? So is this a synthesized attribute? No. But suppose this is A. Is this a synthesized attribute? Right. So any of the children can have appear here, but whatever the attributes that are being used here, it should be the attribute of E or the attribute that are child of E, right? So A is a child of E and A's attribute is used here, that is fine. So suppose this is So is this synthesized attribute or inherited attribute? Synthesized, right? uh, is this synthesized attribute or inherited attribute? Right, you can tell it as a synthesized attribute, because do you see any sign of inheritation here? Is it inheriting any attributes from its parent? No. Okay. Suppose, is it synthesized attribute or inherited attribute? Inherited, because this b dot value, so this b dot value is inherited because it is inheriting from its parent. So for inherited attribute, it can inherit from itself, it can inherit from its parent, or it can inherit from any sibling. So a dot value, a is the sibling of b, right? It can also inherit from any sibling. So is this synthesized attribute or inherited attribute? Okay, so is it inherited attribute or synthesized attribute? Inherited, right? Very good. So here, whatever ever I have said, it is written in bookish language here, right? So when you construct a parse tree, you will have some node, and here the node is written as n, and it will have some children, and children will have some attribute, and depending on how the attribute is being calculated, you will either categorize it as inherited attribute or synthesized attribute. Okay. Now, evaluating an STD is very easy given that you have a synthesized attribute. All of its attributes are synthesized attribute, meaning whatever the tree you have, right? Uh, all the attribute of this tree will be synthesized, right? So it will go from bottom to the top. So if you do uh, depth first search, you can easily get evaluate the value from its child to its parent, then from its parent to its parent, and at the end you can finally go to the top node and evaluate the value. It is very easy, right? So you can evaluate easily by using a depth first search if all the attributes are synthesized attributes. But if the attributes are inherited attributes, suppose this f sorry, this class has an attribute some value, right? It calculates the value from t as well, it calculates the value from f as well. In this case you cannot use depth first search, because when you use depth first search and when you go here, it will only have the value of t, but it will not have the value of f. Okay, so you cannot calculate star here. Okay, so whenever your production having semantic rules, and any of the semantic rules have any inherited value, you cannot evaluate those STT by using depth first search. There might be some other uh, parsing algorithm that you need to use to evaluate them, right? Now let's see a simple example how you can evaluate an STD using depth first search if all of its attributes are synthesized attribute, right? If not all of its attribute are synthesized attribute, you need to evaluate it some other way, right? You can use your eyes to figure out when a value will be transformed from which attribute. By using that you can figure out, but you cannot follow any algorithm that can easily figure it out. Okay, So we'll talk about this later when we study about S attributed SDT and L attributed SDT. For now, let's look at how can we evaluate a simple SDT that has all of its attribute as synthesized attribute. If you look here and if you create a tree, you can see all of its attribute are synthesized attribute. So we need to evaluate this expression, right? So we create the parse tree. First we create the parse tree. So first we need to create this parse tree, right? After creating the parse tree, we need to write the attributes after that, right? So we created the parse tree and we have written the attributes. S has an attribute L dot val, right? And E dot val will write all those attributes. Okay. Uh, let's do this. Right. So we'll write all of the attributes. Now we'll start traversing in depth first manner. So first we reach digit.lexval, right? So we first reach digit.lexval. So F produces this digit, which is 3. Lexvals basically means the value of its lexeme. So when it goes as a token, this 3 is a lexeme, this star is a lexeme, this 5 is a lexeme, right? So the value of lexeme is 3. So digit.lexval will be 3. So after going here, we'll go to f dot val, right? So f dot val is equal to digit dot lex val. So what is digit dot lex val? We'll use this rule, right? So f dot value is equal to digit dot lex val. So what is this lex value? It is 3. So the value of f will be 3 as well. So after that, we have reached this node, right? So for this node, the value of t. So if you see here, the semantic rule is t dot value is equal to f dot value. So we have f dot value as 3. So t dot value will also be 3. So after traversing, we have reached this node. We do not have any rule for multiplication. Then we go to this node. So digit dot lex val. So again, so the we have 3, then we have multiplication, then we have this lexeme. This lexeme is 5. So what is the lexical value of this? The lexical value of this is 5. Then we go to this node. So this node has a value of what? F dot val is equal to digit dot lex val, which is 5. So this is 5. And then we go to this node, t dot val. So what is the value of t dot val? So if you look here, so t produces t into f. So t into f, right? T into f. So this is the rule. What is the semantic rule? T dot value is equal to t1 dot value. T1 value is 3. 3 into f dot value. What is the f dot value? F dot value is 5. So 3 into 5 is 15. So t dot value is 15. Now we go to this node. So this node is basically this rule. So E dot value is T dot value, which is 15. Now we go to this node. There is no semantic rules regarding this node. So we go down this node. Here again, the plus is here, right? The plus is here, and after that, the next lexeme is 4. So what is the value of this digit? Lexical value of this digit, it is 4. And after that, we go to this node, and this node will follow this rule. So what is the value of f? The value of f is 4. Now we go to this node, t dot value. What is the value of t? For this, we will follow this rule. So t dot value is equal to f dot value. So f dot value was 4, t dot value will be 4 again, right? And after that, we go to this node. So basically, we are doing depth first traversal. We are going to e dot value. So what is e dot value? To calculate E dot value, we need to consider this rule. E dot value is equal to E1 plus T. So this is E1, this is plus, and this is T. And the what does the semantic rule says? The semantic rule says E dot value is equal to E1 dot value plus T dot value. E1 dot value is basically 15. So 15 plus T dot value is 4, which gives us 19. So E dot value is 19. And we go to this node. There is no rule for n alone. Then we go to this node, L dot value. So L dot value is equal to, we'll use this rule. L dot value is equal to E dot value. The E dot value was 19. So by using syntax analysis and using some semantic rules, whenever you are evaluating an expression, you can also evaluate the value of that expression, which is 19 in our case, right? So we have evaluated the value 19. Okay, is it clear? Any questions? So the value is 19. Yes. কোথায় 4n ছিল না, দেখেন 4n, what is this? L produces E or N. This L produces E and this N. Okay, this L is producing E and this N. This N is a different entity. It is not with this digit. This N basically signifies the end of digit. It can be dollar sign as well, right? So this is the end of input. This N basically signifies the end of input. Clear? Okay, so do you see any rule that is multiplying any value with n here? No, right? Because this is not the part of the input. This is basically means the end of the input. Clear? Okay. So this is it for today. I am gonna turn off the recording. Do you have any questions? Any questions? Okay.